Over the last decade, global crustacean aquaculture has tripled its output, packing more shrimp and prawns into high-density ponds than ever before to meet surging market demand. In these crowded waters, pathogens find an ideal environment to thrive. Specifically, bacteria like Vibrio multiply aggressively, causing outbreaks that wipe out entire farms. These outbreaks are particularly lethal because of a specific biological trait. Crustaceans completely lack an adaptive immune system. They cannot produce antibodies or develop long-term resistance to specific pathogens through previous exposure. This vulnerability is exploited by conditions like white feces syndrome, or WFS. This gastrointestinal disorder causes the sloughing of cells in the hepatopancreas, the shrimp's primary metabolic organ, effectively starving the animal from the inside out. For years, the industry relied on antibiotics to manage these losses. Today, that strategy is failing as bacteria evolve to survive the drugs, leading to rampant antimicrobial resistance across global production hubs. Attempting to solve this by treating the water with harsher chemical disinfectants often backfires. These chemicals strip away beneficial microbes, leaving the shrimp even more vulnerable to the next wave of opportunistic infection. Securing the global crustacean yield now requires a shift away from pathogen eradication. Instead, the focus has moved toward complex ecological modulation to support the host. A modern high-density pond functions less like a natural habitat and more like a closed-loop crustacean bioreactor. Because of the risks associated with chemical residues, regulatory bodies like the Coastal Aquaculture Authority have established strict lists of approved antibiotic-free inputs for these systems. This diagram illustrates the three pillars of the antibiotic-free bioreactor. It relies on a feedback loop between live probiotics for water quality, metabolic enzymes for feed efficiency, and polyphytoimmunomodulators for host immunity. These are plant-derived compounds that stimulate natural cellular defenses. These biological inputs are not reactive treatments. They are proactive architects. They are used to continuously shape the environment and the internal physiology of the shrimp. This approach moves the timeline of intervention. The goal is no longer to treat a sick population, but to prime the population's defenses before a pathogen can take hold. Reaching absolute pathogen resistance requires engineering the water column, the feed interface, and the host's biology simultaneously. The engineering starts at the bottom of the pond, in the benthic layer. This high organic waste zone is where uneaten feed and feces accumulate, creating a breeding ground for toxic ammonia and Vibrio bacteria. In this cross-section of the pond floor, water column probiotics are active biological competitors. They expand rapidly to physically displace pathogenic clusters from the sediment. This is competitive exclusion. The beneficial microbes consume available space and nutrients, starving the established Vibrio populations. These probiotics also secrete antimicrobial peptides. These are naturally occurring protein fragments that actively target and destroy the cell membranes of harmful bacteria. While suppressing pathogens, these probiotics perform a secondary task. They digest underlying organic pollutants. This biological cleanup significantly reduces the environmental ammonia levels in the pond. Through this dual action, water column probiotics transform the pond from a Vibrio incubator into an environment that is actively hostile to pathogens. This transformation relies on specific microbial strains, such as Bacillus cetullus and Rhodobacter. Bacillus strains act as the primary decomposers, breaking down solid organic waste on the floor. Rhodobacter specializes in processing the dissolved toxic gases that accumulate in the water column. In a commercial pond, these live cultures often degrade in the caustic water before they can reach the target pathogens. To ensure survival, some formulations use nano-silver encapsulation. This creates a protective metallic barrier, allowing the live cultures to navigate the harsh pond environment intact. The nano-silver layer also provides a direct offensive benefit. Upon physical contact, silver ions penetrate and rupture the cell walls of harmful bacteria, neutralizing the threat instantly. Combining specific microbial strains with nanoencapsulation turns generic microbes into precision-guided biological tools against vibriosis. While probiotics manage the external water, the feed interface requires metabolic enzymes. Unlike living probiotics, enzymes are non-living biochemical catalysts that drive immediate reactions. Specific enzymes like cellulase and protease act as molecular scissors. They systematically clip the complex plant fibers in the feed into smaller, absorbable individual units. This action increases feed digestibility by approximately 40%. It optimizes the feed conversion ratio, or FCR, the measure of how much feed is required to produce a kilogram of shrimp biomass. Because shrimp are bottom dwellers, their feed pellets sit on the pond floor. This creates a window where water-soluble nutrients and enzymes can rapidly leach away before the shrimp eats. Farm managers use specialized gel binders to solve this. These binders lock the enzymes, vitamins, and minerals onto the exterior of the feed pellet, holding them in place until the point of ingestion. Mastering this interface ensures the shrimp absorbs the maximum possible energy from every pellet, redirecting metabolic power from difficult digestion into physical growth. Managing a farm requires balancing formulations designed for rapid growth against those engineered for disease resistance. Growth formulas prioritize dense phytoproteins and omega-3 fatty acids to accelerate the molting cycle. This can reduce the total cultivation period from 120 days to just 90. Resistance formulas focus instead on antiviral and antibacterial phytocompounds. These ingredients shift nutritional resources towards supporting the immune system. Using a high-growth formula during an active bacterial outbreak is dangerous. It forces the shrimp to expend energy on molting when its metabolic resources are needed to fight the infection. The standard protocol involves a strategic rotation. Defense formulas are used to arrest the disease and stabilize the population, followed by growth formulas to recover the lost biomass. Modern aquaculture relies on this dynamic biochemical throttling, trading peak growth for survival during periods of environmental stress. Without the ability to produce antibodies, shrimp must rely entirely on immediate innate cellular responses to survive an infection. Polyphytoformulations deliver concentrated secondary plant metabolites. These are natural compounds designed to trigger and sustain the shrimp's innate cellular defenses. The active agents in these formulas are highly specific: flavonoids, carotenoids, and potent botanical antioxidants. This data visualization illustrates the effect. Following the introduction of these phytochemicals, the shrimp's total hemocyte count upregulates. Hemocytes are the primary defense cells in crustaceans, analogous to white blood cells in vertebrates. At the same time, the introduced antioxidants neutralize reactive oxygen species, or ROS. These are harmful molecules generated by the physiological stress of environmental crowding. These polyphytocompounds act as a biological update for the shrimp's innate immunity, priming it to attack invaders before physical symptoms ever appear. The primary internal defense is the prophenyl oxidase, or ProPO, activating system. This is a complex biochemical chain reaction used by crustaceans to neutralize pathogens. Phytocompounds in the feed trigger this system. Once active, the ProPO cascade physically encapsulates and suffocates invading bacteria directly within the shrimp's tissue. Structural defense is equally important. The shrimp's exoskeleton is its first line of protection, but it must be shed and rebuilt during the grow-molt-grow cycle. Pathogens often exploit the post-molt soft shell phase. During this window, the shrimp is physiologically exhausted and lacks its protective armor. Minerals like calcium and magnesium accelerate post-molt calcification. This reduces vulnerability by turning the translucent shell into a hardened barrier more quickly. Surviving in a high-density pond requires this combination of an aggressive internal chemical defense and a rapidly hardening physical armor. This timeline chart maps the 72-hour recovery seen when combining water probiotics, enzymes, and polyphytoimmunomodulators during an active outbreak. We see a steep decline in pathogen load as the host's appetite and cell counts return to normal levels. As the infection clears, the hepatopancreatic tubules regenerate and the gut microflora stabilizes, allowing the shrimp to resume regular feeding. Once mortality is arrested, the intervention shifts from high-concentration therapeutic dosing to a steady-state prophylactic maintenance schedule. This establishes a stable biological equilibrium, replacing the volatile boom and bust cycles seen in ponds treated with traditional antibiotics. In an open earthen pond, the total eradication of Vibrio is mathematically impossible. The bacteria are a permanent part of the aquatic environment. However, by engineering biological dominance, keeping pathogens suppressed and the host resilient, commercial crop loss becomes preventable. Executing this strategy requires a strict operational checklist. Farm managers must continuously monitor ammonia and oxygen levels to time their probiotic dosing accurately. They must physically verify the integrity of feed binders. If the binder fails, the phytochemicals and enzymes will wash off into the sediment before the shrimp can ingest them. Daily observation of the biomass is critical. Early indicators, such as reduced feeding or lethargic swimming, provide the first warnings of molting stress or systemic infection. Dosage must also be scaled proportionally. As pond organic load increases over the 90-day culture cycle, the level of immune support must rise to match the environmental pressure. Scaling the dosage to match the pond's organic load maintains survival rates while ensuring compliance with global export markets that mandate zero chemical residues. High-density aquaculture is moving away from the goal of sterilization and toward the goal of maintenance. The long-term profitability of the industry now depends on this shift from brute force chemistry to multi-layered ecological engineering.